Dun, dun, dun. I know identities are intimidating. I know they usually carry a lot of marks for one question. I know it's something that requires experience and quite a bit of foresight, but I know that you have what it takes to do well. So let's start off by just having a summary page of all the identities we know. Have a look at them. There's many actually, but look how far you've come. The cos compound angle formula, the sine compound angle formula, I've just condensed those obviously to consider the plus and minus versions of both. Then we've got all the green rectangles. Those are your double angle identities. My favorite thing about double angle identities is, well, there are two things. Firstly, sine 2x only has one option. It is always equal to sine x cos x. So if you see a sine 2x, you must know you can change it to one thing and one thing only. So you may as well go for it. But cos 2x has three different options. The other thing that I love about the double angle identity for cos 2x though is that cos squared x minus sine squared x can always be factorized because it represents a difference between two perfect squares. So you can always factorize that identity into cos x plus sine x, cos x minus sine x, and this will help you when proving left hand side equals right hand side, because sometimes we can cancel whole brackets. So that's a wonderful thing. Then don't forget what we learned in grade 11, and that is that tan is sine over cos. Also, only one option for tan. So whenever you see a tan x, change it to sine over cos and see where it leads you. And then sine squared x plus cos squared x equals 1, which is also a fabulous identity, because remember, when you see a number 1, you can potentially replace it with sine squared x and cos squared x, and that can potentially lead you to a trinomial, but I'll discuss that on the next slide. Right, just some general tips for proving identities. Remember that if you are given an equation that you need to prove true for all variables, you are welcome to work on the left-hand side to a point and then on the right-hand side up to a point. If those 2 points that you reach are the same as each other, you can conclude that the left-hand side equals the right-hand side. Sometimes people even like to split their page into two and work into 2 columns and work on the left-hand side and then work on the right-hand side. So that is possible, but generally we choose the side that is a little bit more detailed, that gives us more options in terms of applying our identities that were given on the previous page. Beware of trying to tackle an identity and trying to apply all the rules you know in one step. So do not do too much at once. For example, cos of 2 theta has 3 options. Don't apply any one of those options until you are confident about the value of the one that you end up choosing. All right. Also, please don't mix your algebraic or what do we call it? Our normal orders of operation kind of laws to trigonometry. For example, cos 2 theta plus sine 2 theta. That 2 theta is an angle in itself. You can't factorize it and be left with a cos theta plus sine theta, because that 2 is not the numerical number 2. That 2 represents whatever degree the angle is. You're doubling an angle. So please don't make that error. I will cry if I see that. And then be aware of the need to find an LCD when dealing with more than one fraction. This will often lead you to have more than one term at the top of a fraction, which ends up cancelling with brackets as well. So LCD is usually a very good step to apply. So just keep that at the back of your mind when tackling these kind of questions. So here's my golden tip. I've seen it time and time again, and I think it is an excellent thing to just make note of and perhaps memorize it along with your other identities. 1 plus sine 2 alpha, let's break that down into, when you see this 1 plus 2 sine alpha, the 1 the sine of a double angle. I want you to think trinomial. Why? Because if you break down the 1 into sine squared alpha plus cos squared alpha, and you break down the sine 2 alpha into 2 sine alpha cos alpha, you can use those 3 terms right there underneath the blue arrows to create a trinomial. If we pop the sine alpha cos alpha in the middle and we split the square's identity to be on either side, you can factorize this trinomial and once again create brackets that will most likely be able to be cancelled, leading you closer to your answer, your left hand side equals right hand side. Righty-yo, are you ready for an example? So this first example looks relatively scary because of those exponents, but when you break it down and you lay out your options, you see that it's really not that bad. I'm sure you've recognized that on the right-hand side of this equation, there is a cos double angle identity. So let's keep the 3 options available at the back of our minds. Hold your horses. Don't try and apply any one of these options just yet. Save it for later. Let's have a look at this left-hand side and see if we can work on this slightly. I hope you've recognized the difference between squares. So we can break this down into 2 brackets, cos squared alpha minus sine squared alpha and cos squared alpha plus sine squared alpha. And da-da-da-da-da-da. I hope you recognize that this right bracket is just the square's identity. So in our next line, we can replace it with a 1. Now if we have a look at what's in front of us, cos squared alpha minus sine squared alpha, I'm sure your eye has been drawn to the top right of the screen where you see the double angle identity for cos. We now know which option we are dealing with. So we can merely replace that with cos 2 alpha, which is the right hand side. It's as easy as that. Next example, we are required to show that this scary looking fraction is equal to sine x minus cos x. Now if you have a look at this right hand side, there's not much we can do with it, so let's work on the left hand side for now. The only thing that rings a bell is the double angle identity for sine, so let's go ahead and apply it. Instead of writing sine 2x in our next line, we can write 2 sine x cos x. Now, when you see that formation, I want you to think trinomial, trinomial, trinomial. Why? Because along with the sine x and cos x that are together, you can apply the square's identity to that little 1 right there. If you don't see what I've done in this little line, I want you to look at sine squared x, and then there's a big gap, but the cos squared x is at the end, and sine squared x plus cos squared x gives you the 1 in the previous line. Now we have a trinomial that we can factorize into sine x minus cos x times sine x minus cos x, and what do you know? The brackets cancel and we end up with the right hand side. This last example is one where I'd like us to work on the left-hand side for a while and the right-hand side for a while. You usually do this when both sides have identities that you can apply. For example, the left-hand side has a tan, and you should know that tan is sine over cos. So if you have a look at what I've done here, I've taken that fraction line where 1 minus tan is over 1 plus tan. That fraction line has changed into a divide sign. And the 1 in the numerator, I just wrote as 1 over 1, and the 1 in the denominator, I wrote as 1 over 1, so that it's obvious to see that in each bracket we have 2 terms, and when you have 2 terms in a bracket, you can find an LCD, which is cos A. If I apply cos A, 1 over 1, 1 required me to multiply by cos A, what you do at the bottom, you do at the top. So my fraction on the left is cos A minus sine A all over cos A. That comes from the bracket on the left-hand side of the divide sign. And then the bracket on the right-hand side of the divide sign simplifies to cos A plus sine A over cos A. Of course, when you have a fraction divided by a fraction, we tip and times, and voila, our cos A's cancel. But at this stage, we can't do much else. There's no other identity that can be applied here. So let's leave that for now and perhaps work on the right-hand side of this identity. Once again, we have the cos double angle identity that has 3 options. So I'm writing them down to keep them at the back of my mind, but I'm not going to apply them now. However, at the bottom, we've got sine of 2a, and I hope you're thinking what I'm thinking, trinomial, trinomial, trinomial. If we apply the previous questions techniques, I am skipping a little bit of a step here, but I hope you realize I've converted that 1 into sine squared a plus cos squared a. If you're not following, go look at the previous example. And then the sine 2a has been converted into 2 sine a cos a because of the sines double angle identity. And now we can factorize that trinomial into being sine a plus cos a times sine a plus cos a. So that should ring a bell, top right. Once again, we can apply the difference between squares of the cos double angle identity and then factorize that bad boy and cancel the relevant brackets to get what we got to on the left-hand side as well. If you have a look at the left-hand side's final point versus the right-hand side's final point, you'll see that we indeed have proven the left-hand side and right-hand side to be equal. Now it is your chance to go and complete all of the other questions. I've just done 3 of them for you. I've done 3 of the questions from exercise 4.7. Do as many of them as you can, and please read over the 3 examples just before the exercise to reinforce these concepts I've covered now. Good luck!